We present Sparsifiner, learning sparse instance-dependent attention for efficient vision transformers. Vision transformers has emerged as dominant model for fundamental vision tasks. However, scaling vision transformers to handle a large number of tokens is challenging due to the quadratic computational complexity of multi-head self-attention. To this end, previous methods explore different attention patterns by limiting a fixed number of spatial nearby tokens to accelerate vision transformers' multi-head self-attention operations. However, such structured patterns limit the token-to-token connections to their spatial relevance, which disregards learned semantic connections from full attention. In this work, we propose to learn instance-dependent attention patterns by devising a lightweight connectivity predictor module that estimates the connectivity score of each pair of tokens. Prior works have largely taken two approaches to improve the computational efficiency of vision transformers. The first, token pruning methods such as dynamic VIT progressively remove tokens at different stages in the network. However, quadratic computational cost remains in shallow layers, and introducing token pruning into those layers results in a significant accuracy drop. Another approach involves pruning individual attention connectivity. In Big Bird, fixed attention patterns are combined with random connectivity to model long-range dependencies. However, these predefined patterns limit the capacity of self-attention to a fixed subset of tokens. To address these challenges, we introduce Sparsifiner, which learns to compute sparse connectivity patterns over attention weights that are both instance-dependent and unstructured. The instance-dependent nature of the attention pattern allows each token to use its limited attention budget of non-zero elements more efficiently than fixed patterns. Furthermore, Sparsifiner improves attention pattern flexibility compared to token pruning by pruning individual connectivities rather than entire row and columns of attention masks. This approach allows Sparsifiner to reduce flops in the early layers of the network without significant top-line accuracy degradation. By pruning connectivities based on image content, Sparsifiner generates prior approach to sparsify multi-head self-attention in vision transformers, producing a favorable trade-off between accuracy and flops. Sparsifiner consists of a normal vision transformer as a backbone with sparse attention module at each layer. At each layer of vision transformer, Sparsifiner replaces the dense attention module with a sparse attention module. Input tokens will feed into a connectivity mask predictor. For each query token and each attention head, the mask predictor will estimate the connectivity score between tokens and produce a sparse attention mask, indicating corresponding attention connectivity. Then a sparse multi-head self-attention and a sparse attention value product are computed based on the mask. In both training and inference, we generate sparse connectivity masks by restricting the number of connections predicted by the mask predictor according to a hyperparameter, budget size b. Ideally, Sparsifiner reduces quadratic complexity to linear, considering b is small constant. To efficiently generate attention connectivity score, which have quadratic complexity, we compute a sparse, low-rank approximation of dense attention in a naive transformer. This approximation then serves as the connectivity score. Specifically, we compute a dense, dimension-reduced attention A down by down-project K matrix to a lower dimension using a learned projection matrix. Then sparsify A down to obtain a sparse and skinny attention matrix. The attention connectivity score is computed by up-projected skinny sparse attention. The up-project matrix is learned and enforced to be sparse. Computing the connectivity score map using a sparse matrix product costs less than O(n)². In practice, those two matrices can have a sparsity of over 85%. The final score map is a low-rank approximation of dense attention, with most of the element being 0. Then attention mask is computed by simply applying top K over the connectivity score. For each attention head and query token, we compute a separate mask. We adopt the standard quasi entropy loss over predict class distribution and ground truth to train Sparsifiner. To speed up the convergence of Sparsifiner, we use another dense backbone vision transform model as a teacher within a knowledge distillation framework. We introduce attention distillation loss that minimize the Euclidean distance between the connectivity score map and teacher dense attention. To enforce the sparsity of the up project matrix, we use the L2 regularization. In our experiments, L2 gives better training convergence than L1 with sufficient sparsity. To improve the speed of convergence, we propose a two-phase training strategy. In the first phase, we freeze the backbone model and train the mask predictor with attention distillation loss and L2 regularization only. We found that this setting helps the mask predictor to learn the up-project basis matrix quickly within 5 epochs. After the first stage of training, we apply a threshold on the learned basis to point noisy values. In the second phase, we freeze the connectivity mask predictor module and fine-tune the backbone for another 40 epochs. We train and evaluate Sparsifiner on ImageNet. Compared to the full attention baseline DEIT, Sparsifiner can achieve over 73% reduction in multi-head self-attention flops with minor accuracy drop. We compare Sparsifiner with the state-of-the-art token pruning method. Sparsifiner achieves superior performance and accuracy trade-off compared to the baseline. We visualize the sparse attention map compared with naive full attention. Sparsifiner generates different sparse patterns for different tokens in the same image. The sparse attention retains the most salient relations for a given token while discarding noisy background relations. We visualize the up project matrices. Sparsifiner naturally learns a set of sparse bases resembling 2D Gaussians. Low-rank attention, such as lymphoma, produce a coarse attention map. Conversely, Sparsifiner's full-rank sparse attention bears a closer resemblance to a dense attention. In summary, we present Sparsifiner, a computational efficient method to learn sparse instance-dependent attention in vision transformers. We hope that this work can help accelerating future research in sparse algorithms for transformers.